This is the Maple lesson on random numbers and random polynomials. So if you just choose at random a number, well, it's hard to do that, but in Maple there is a function. It's rand around parentheses, and this produces a random 12-digit positive integer. So, this is a random 12-digit positive integer. If I do it again, I get another random 12-digit positive integer. It will never be the same. Suppose we do this 10 times in a row. Let me make a loop. For n from 1 to 10 do, and rand So these are randomly produced 12-digit numbers. Now you might say, what about this number? It only has, how many? 1, 2, 3, 11 digits. Well, it really is a 12-digit number, but the first digit is a 0. So you can have any number of digits up to 12. If we do it again, we'll produce 10 more random numbers, and it's a completely different list. Now, suppose you want to know, for example, what's the factorization of these integers? So I could do the following. Let's say for n from 1 to 10 do. So I need to give this number a name. I'll call it a. So a is going to be this random digit. And then I factor a. So this little program will generate 10 random numbers and then factor them. Here they are. Interesting. Now look, this one, when it factors, there's only one factor. This guy's actually a prime. That's interesting. Let me just check that. Is prime. I can't put random now, it would give me a different number, but that's exactly this number. True, this is a prime. Suppose we wanted to generate, let's say, 100 random numbers and see if they're primes. For n from 1 to 100 do. A equals random number up to 100, RAND. Is it prime? Wow. Let's see. Ooh. Yeah, it's a lot of numbers. 100 numbers at random. You get a lot of falses. Any truth? Well, it just shows you that prime numbers are rare. Instead of having to run through the list, let's do this slightly differently. Suppose I want to count. So here's what we're going to do. Count the number of primes in a list of 100 randomly chosen 12-digit positive integers. Right. Oops, let's try to spell it right. Integers. Yeah. So Instead of this, which is what I did a moment ago, let me introduce a variable that will do the counting. Let's say I'll call it n. And I'm going to start with n equal to 0. And then for each number from 1 to 100, let a be this random number. Let's write it like this. If a is prime, so if a prime of a is true statement, then what do we want to do? Add 1 to n. Replace n with n plus 1. And that's the end of the if. And that's the end of the do. So I start with n equals 0. And going from 1 to 100 means I'm going to generate at random 100 randomly chosen integers. And if a of this randomly chosen integer is prime, I got 1 to n. So when I'm done, n is the number of primes in this list of 100 numbers. And maybe I'll just print out a statement. Print there are n primes. Let's see if this works. Let me just take this out for the moment. So it's doing this calculation. Here's the list of 100 randomly chosen integers. And how many are primes? 4 of them. Huh. Which 4 though? I don't know. So maybe I should say this. If n is prime, then if a is prime, print a, and then the number, and at the end, let's just type out n. Let's see what happens now. Sure everything is clear. Let a be this random number. If a is prime, then print a, semicolon. Let me try it like this. And let's just do it for the first 10 numbers so we don't take so much time. Let's just see what happens. So here are 10 random numbers, and none of them is prime. Let's try 50 numbers chosen at random. One is prime. I see. Let's see. So it's printing out all these numbers. Let's try this. Print a is prime. Wow. So in this batch of 50 numbers, 3 of them are prime. That's the number 3 down there. And here, prime, prime, and prime. Let's try something else. If I put semicolons, if I put a colon instead of a semicolon, that's perfect. So now it's only printing out when we get a prime. So this is generating 50 numbers. I don't see what they are, but these 2 are primes. That's kind of interesting. Now, suppose you want to generate a number at random, not a 12-digit number, but let's say a number between 10 and 20. So for that, we have the following function, rand, colon, 10, I think this is the way to do it, 10, 20. And so let's see. The function rand a dot dot b, or u dot dot v, generates a random integer between u and v. Let's see if that really works. So let's try to generate a random number from 10 to 20. Well, that's just generating. Let me give this a name. I'll call it capital R. So if I write R, parentheses like that, I get the number 11. If I do it again, I get the number 13. Let's say I do it 10 times. For n, from 1 to 10 do. And this is going to generate and do 10 random numbers between 10 and 20. There they are. They're not all different because they can't all be different. Let's see. If I do this, yeah, the first, second, third, this is just sort of enumerating them. Suppose I want a number between 10 and 100. So R will be a random number between 10 and 100. Oops. Yeah, here they are. 10 random numbers from 10 to 100. Let me do it again. There are 10 different random numbers. Let me do it again. Another 10 different random numbers. So you can give yourself a range. It's kind of interesting. And everyone who does this will get a different sequence. So it's really kind of cool. Now, there's something else you can do. So Maple also generates a random polynomial. And let's see, rand poly. Let's see what happens if I enter that. Let's see, what is one wrong there. This is what I want. So I have to say what I want the variable to be. So let's say I want the variable to be x. Rand poly, a polynomial where x is, aha, we get a random fifth degree polynomial. So Maple also generates random polynomials of degree at most 5. Let's generate a list of them. Let's see. So for n from 1 to 15, do random polynomial in the variable x. Haha, here they are. They're all degree 5. Sometimes they'll be degree less, but it's certainly a degree at most 5. So suppose you wanted to analyze a random polynomial. Let's try something else. Let's call this random polynomial P is this random polynomial. So let's try to factor P. That'd be kind of interesting. Looks like none of these polynomials actually factors. Let's double check. Yep, each of these is irreducible. That's kind of interesting. Suppose we wanted to analyze the graph of a random polynomial. That means find where the function is increasing, decreasing, concave up, concave down. So find where this polynomial function is increasing, decreasing, concave up, concave down, and has local maxima and minima and inflection points. So this is the basic thing we do in Calculus 1 when we're analyzing a function. So suppose I let f be this random let me call it P. Actually, let's get a random polynomial of x. There it is. And suppose we let f be the function x goes to, let me just copy and paste that, exactly this. So I just generated a random polynomial. What does the graph of f of x look like? Looks like that. Let's see. The interesting part is between, I don't know, -4 and 4. So let's just graph it. Looks like that. Suppose I go from -2 to 2. There we are. So what's going on here? Where is it increasing? Where is it decreasing? So the derivative of f is this fourth degree polynomial. And where is that equal to 0? So that's f solve d of f of x equal to 0 for x. So this has two critical numbers. All right. Let me call this Cn, for these are the critical numbers. So the first one, Cn1, is that, and the second critical number, Cn square brackets 2, is that. So let's look at this from, let's plot this again. Instead of, let's plot it from maybe minus 0.5 to 1. Oops. So you can see when you blow it up in here, it really does have one local maximum or relative maximum and one relative minimum. And these terms are used interchangeably, local maximum or relative maximum. So when you blow it up, you can see here there's a local max, or here there's a relative min. Here it's increasing, decreasing, and increasing. Let's just look at the concavity. What is the second derivative of this function? D at f of x d at 2 of f. That's the second derivative. And where is this positive? Where is this negative? Where is it 0? Let's see. So suppose we try to find where the second derivative is 0. It has just one 0 at 0.26. And let's see if Maple can do this. I'm not sure. Suppose we want to solve the inequality. Where is the second derivative positive? Yeah, I don't think f solve will work. So we get that, but let's see if we can convert that to decimals. So the second derivative is positive from 0.264 to infinity. So the graph is concave up from, let's just say, on the interval, spell it properly, yeah. And if you do the analogous thing for where the second derivative is negative, and We convert that to decimals. We get this. So the graph is concave down on this interval. And we have an inflection point at x equal to, this is the point, where the concavity changes from concave down to concave up. Now, we analyze this for a random polynomial. So let's repeat all this. Let's do it again. I'll do it without even, well, repeat. Good to spell things properly. Repeat with another random polynomial. See if I can call it something like G. Yeah, that's my random polynomial. And or maybe I'll call it something different, Q. Because I'm going to get a different polynomial now, right? Q. And let's define the function G, which is x goes to well, let's just call it Q and see what happens. So let's plot Q. Well, nah, I'd rather have it as a function. So G is going to be the function x goes to Q. So G of x is equal to this, right? This is our random polynomial. Suppose I plot G of x. Oops, plot G of x, comma x. That's what it looks like. I'm not sure that's really what it looks like because, no, that's right. Let's plot it maybe from -5 to 5. Oops, what happened? Plot G of x, x goes from -5 ... 5. Actually, what's interesting, it seems to be between maybe -3 and 2. I just want to blow it up a bit so I can see what's going on. Oh, wow. So it comes down, seems to go up, and then down again. Maybe I'll go from -2.5 to 1.5. This is kind of interesting. Looks like maybe it only has one relative minimum and one relative maximum. So let's see. That's F solve. We want to find where is the derivative of G of x equal to 0. Solve that for x. Why doesn't it want to give me an answer? d of g of x. Oops. What is going on? Let's start this process again. We'll repeat with another random polynomial. Ah, that's what it is. So that's my polynomial. When I plot it, I get something that looks like this. Maybe I should go from -2 to 3. I go from -1 to 2. It's kind of a strange function. What is the derivative of this polynomial? Why is it giving me 0? This is the function g, derivative of g of x. G of 0 maybe I should have done it the way I did it a moment ago. So here's a random polynomial again. I'm just going to copy and paste. So that's my function. That's g of x. And when I plot it, it looks like that. Minus 60,000 to 600,000, 200,000. Let's just blow it up from -3 to 3. Interesting. Maybe I'll just do it from -2 to 2. -1 to 2. -1 to 1. It looks like this function maybe has no relative minimum or maximum. Let's see, what is the derivative of g of x? It's that 4th degree polynomial. If we try to find where is the derivative of g equal to 0, solve that for x, we get no result. Suppose we want to find where is d of g of x greater than 0. Solve that inequality for x. It's all x. So the derivative of the function g of x is always positive. So g of x is increasing and has no relative maximum or relative minimum. There's no relative maximum or relative minimum. But it could still have an inflection point. So let's see where the second derivative is positive. So what is the second derivative? D at 2 of g of x. That's this 3rd degree polynomial. And let's see. Let's find where the second derivative is greater than 0. This just says stop. Okay, well, we get some interval, and it's converted to decimals. So this function is concave up on this interval. G of x is concave up, where the second derivative is positive, which is on the interval, on that interval. So here is concave up. Where is the second derivative negative? On this interval. On the interval from minus infinity to that number. And where is the second derivative equal to 0? Let's use f-solve for that. Where is the second derivative equal to 0? Exactly there. So g of x has an inflection point at x equal this number. And let's see, I have to save this at some point, but so this is how we generated a random polynomial. We looked at the graph of the corresponding function and we analyzed it. But everyone who does this will get a different polynomial. Every student will have a different polynomial to work with. But the analysis is always the same. So let me save this. No. That's really interesting. So this is the last topic that we're doing. And there'll be a homework assignment on this, and we'll be done. Okay.